Bioactive glass is a specialized class of glass ceramic materials that are designed to interact biologically with living tissues, promoting bonding and stimulating regenerative processes. It was first developed in 1969 by Larry Hench and colleagues, who discovered that certain silica-based glass compositions could form a direct chemical bond with bone. Unlike conventional inert biomaterials, bioactive glass is able to form a hydroxycarbonate apatite (HCA) layer on its surface when it comes into contact with physiological fluids, which is chemically and structurally similar to the mineral phase of natural bone. This unique property allows it to integrate with living tissue without the formation of fibrous scar tissue, making it a highly valuable material in biomedical applications. The composition of bioactive glass typically includes silica, sodium oxide, calcium oxide, and phosphorus pentoxide, though variations have been developed to optimize bioactivity, mechanical strength, and processing characteristics. When immersed in body fluids, the surface of the glass undergoes ionic exchange, dissolution, and precipitation reactions. These processes result in the formation of a biologically active layer that encourages the adsorption of proteins and subsequent attachment, proliferation, and differentiation of osteogenic cells. The bioactivity of the glass is highly dependent on its composition and surface area, with certain formulations, such as the widely studied 45S5 bioglass, showing particularly strong bonding with bone tissue. The most prominent applications of bioactive glass are in medicine and dentistry. It is used extensively in bone regeneration, as a bone graft substitute, and as a coating for metallic implants to improve their biocompatibility and osteointegration. In orthopedics, bioactive glass can be used to repair bone defects, promote healing in spinal fusions, and support regeneration in maxillofacial and craniofacial surgery. In dentistry, it is applied in periodontal repair, alveolar ridge augmentation, and is a component of restorative dental products. Bioactive glass is also used in the production of bone cements and composite scaffolds for tissue engineering, where it serves not only as a structural filler but also as a source of ions that stimulate cellular activity and angiogenesis. Beyond hard tissue applications, bioactive glass has shown promise in soft tissue repair and wound healing. Certain formulations release ions such as silicon, calcium, and boron that exhibit antibacterial and angiogenic effects, which can accelerate tissue regeneration and reduce the risk of infection. This has led to the development of bioactive glass-based wound dressings that can treat chronic wounds, burns, and diabetic ulcers. The antimicrobial effect of bioactive glass is particularly valuable in clinical contexts where bacterial resistance is a concern, as its mode of action is based on local pH changes and ion release rather than conventional antibiotics. In scientific research, bioactive glass is studied as a model system for understanding biomaterial tissue interactions and for developing next-generation regenerative therapies. It has been incorporated into porous scaffolds produced by additive manufacturing and sol-gel processes, enabling tailored porosity and controlled ion release for advanced bone tissue engineering applications. Researchers are also exploring doped bioactive glasses, where ions such as strontium, zinc, copper, or silver are introduced to enhance osteogenesis, angiogenesis, or antimicrobial activity. Furthermore, bioactive glass nanoparticles have been developed for drug delivery and controlled release systems, expanding their potential in regenerative medicine and nanomedicine. Industrial applications of bioactive glass are primarily concentrated in the biomedical sector, but its properties have also attracted interest in other fields. For example, its antimicrobial and bioactive nature has made it useful in consumer healthcare products, such as toothpastes for remineralizing enamel and reducing dentine hypersensitivity. The material has also been tested for environmental applications, such as water purification and as a component of bioactive coatings with self-cleaning and anti-fouling properties. Overall, bioactive glass represents a unique class of functional materials that bridge the gap between inert biomaterials and biologically active substances. Its capacity to stimulate tissue regeneration, bond directly to bone, and provide antimicrobial effects makes it a cornerstone of modern regenerative medicine and an active area of research in biomaterials science.